Hello, welcome to Magnetic Fields. Going to look at cyclotrons this time, and hopefully in your future endeavours you may come across some cyclotrons in your work, particularly if you go into medicine. So what is a cyclotron? Well, it's a physics machine that's used to accelerate charged particles, and it consists of what are called two D-shaped cavities called Ds. That's pretty original, isn't it? Where the particles cross a region between the Ds and experience a high voltage that accelerates them. So it's a combination of electric fields and magnetic fields again, and this might make sense until we get a couple of diagrams under our belt. And so what happens is that as the particles cross this high voltage, they get accelerated, but they're only in the high voltage for a short period of time, and then they find themselves in a magnetic field, and that causes them to go in a circular path, and they come back into a high voltage and they get accelerated. So there's a phase of getting accelerated more, and then they get faster and faster, and eventually they'll exit the cyclotron with a very high voltage. And these particles are then used to collide with specific targets. And you think, well, why might we do that? Well, we might do that for physics experiments, but we also do it to generate medical isotopes. And it's the major way of making medical isotopes that doesn't rely on having a nuclear reactor around, because not every country or place or region has a handy nuclear reactor. So this is what they look like. There's a D, as you can see. This is the top view, and there's another D. And what the Ds have is they have a magnetic field. One end is if we look from the side, one end is north, one is south, and each D. So there's really 4 Ds altogether with a gap in between. And what happens is you introduce the particle here, and this is the region where there's a pulsating electric field. And so this particle is, let's say it's an electron, as it says down here. So this side would be made positive, so the electron would experience force due to the electric field that causes it to accelerate in a straight line, but then it finds itself into this magnetic field, so it then goes in a circular motion with a constant velocity, because again this is all evacuated. It then finds itself in the electric field, but the electric field has reversed, so it has this sort of pattern, and it gets accelerated again, so it comes out faster. It's the same mass, but it's faster, and the same strength magnetic field, so it has a bigger radius, and so it loops around like this, getting progressively larger and larger radiuses until it's ejected with quite a high velocity, because it's gotten faster and faster. Keeps getting that push from the electric field. This is another diagram just showing the sides-on view, and so the magnetic field is constant and is usually provided by electromagnets. Usually there's a thing called a yoke, which is a huge steel structure, and that's basically designed to stop it from flinging itself apart, and to be able to stop the two magnetic poles getting too close to each other. Because if we go back, you've got a north and a south defining the magnetic field. Now these guys just want to snap together, so something's got to hold them apart. And the stronger the magnetic field, the greater the force of attraction between these guys. And this is why, if we go back, you have to have these big yokes to stop the two magnets from slamming together. Anything else in there? There's your ion source, so you can put your ions, your charged particles in there, and then these are the Ds. And they were really first used in what was called the Manhattan Project, and the Manhattan Project was the project during the Second World War to develop the atomic weapons, or the atomic bomb. And this is a cyclotron here. You can see the scale of it by these chaps, and there's the yokes holding in the Ds. and this was used to separate isotopes so they could make pure plutonium and uranium and the various other isotopes they needed to have a bomb, basically. And this is one of the bombs. This is one of the earliest bombs just hanging there, ready to be exploded. And so it's a period of physics that was very important because major advances in atomic physics occurred at that time. Whether or not you agree with the atomic bomb or not, that's all a bit of history. So we know these things. And what was interesting is I found some photos of one guy was actually commissioned to take very, very, very super fast photographs of the atomic explosions. And so he had to actually design a camera that could survive the atomic blast because the cameras weren't very far away, survive the radiation, the sudden flash of radiation, survive the heat, survive the shock, and still take photos at super, super fast speeds, and actually show what's happening, because they were interested in what this is the bomb after it's exploded, this ball of hot plasma and stuff was doing, and the shapes and the expression of the actual explosion, because it happened too quickly for the human eye and for normal movies. And so these are some frames of there's an atomic weapon on a tower above, and there's guy ropes coming down here, and you can see the plasma develops these weird and wonderful shapes, and it actually follows the guide ropes down until it becomes this sort of ball of plasma. Really quite amazingly surreal photographs. Whether or not they learnt much from it is another question. There's another one. There's the tower. This is within fractions of a second of it exploding. It's just a massive sun, but really interesting shapes and things happening. There's another one as well, and really bizarre ones, so you can get the scale of some of them. Okay, and this is what it looks like afterwards. Fairly impressive explosions in terms of the scale of things, all related to the fact that they required cyclotrons to actually purify the isotopes. And this is how they used to watch atomic blasts in the 1950s. Pretty common event, so they put out the deck chairs, sit down, get a bit of a suntan, and watch an atomic explosion. So the modern cyclotron, what does it look like? Well, it looks like that. It's all encapsulated. It comes from a factory that makes these sort of precision instruments, and you basically put it in the bottom of a hospital and you can make your medical isotopes. Just to get a scale, these are some chaps that are installing it or operating it, so it's not very big. It's been condensed down to the bare minimum size that you need to do what application you need. This is a research cyclotron, so you can see the yolks and the Ds are significantly bigger. And there's the actual beam coming out of the cyclotron, and in this case, because all this is happening in a vacuum, and then when it comes out to the air, the charged particles hit the air particles and cause an iridescence that you can actually see. They wouldn't normally do this, they're just showing that they could, I think. This is historical ones. Of course, the Russians got involved because they were making their own bombs, so they made their own cyclotrons. This is a large cyclotron, so these are individual yolks holding the whole Ds together, and this is a massive one, and that's the cyclotron there, and these huge massive amounts of steel are to keep these two magnets from coming together, basically. And this is all cooling apparatus and stuff, so fairly impressive. And the modern small d has these interesting shapes to make them fit together well as well. There's a research one, so they come in all sizes and shapes. You can even stand next to one and have your photograph taken. So in the next video we'll look at particle accelerators, so that should be interesting. See ya.